Hi, this is going to be the introduction to chromatographic separations. In this video or screencast, I'm going to try to emphasize some of the basic terminology of chromatography and the fundamental principles about how an analyte or molecule interacts with stationary and mobile phases, how this causes separation, and some of the key fundamental math that we use to describe this. I'll try not to focus on every step of the math, but on some of the most important things. With these fundamentals comes into the concept of what a plate height is to describe the efficiency of separation, and also what the resolution between two peaks are. Finally, I'll wrap up with a few comments about the general elution problem and about how we can do qualitative and quantitative analysis using chromatography. So what is chromatography? Let's start with some terminology and a discussion of what the general types of chromatography are. So chromatography is simply a fancy word for separation of molecules. We have a mixture of components, usually this is chemicals, biological species, medicines, metabolites of medicines, and we want to separate them. We do this by passing them over a stationary phase, which is usually a solid or liquid, and we have the molecules carried by a mobile phase, which is then usually a liquid or gas. It is the distribution of the components in between these two phases that causes our separation. We can classify chromatography into two general types. There's column chromatography, which occurs in a tube or column, and there's also planar chromatography, where our stationary phase is flat, like a piece of paper or a plate. If you've done thin layer chromatography, that's planar chromatography. Maybe you've put a marker on a piece of paper and gotten it wet by mistake or intentionally and seen the colors spread out. Well, that was chromatography on paper. You can only do liquid chromatography with planar chromatography, and so most of our discussion here is going to focus on column chromatography, where you could do liquid chromatography, gas chromatography, and or supercritical fluid chromatography. And these are all defined by what the mobile phase is. So this is a more detailed classification of the methods where we have our gas chromatography, liquid, and supercritical fluid, and then each of them has a specific method that goes with it. And it has to do with what the stationary phase is. In the case that you have a liquid adsorbed or bonded to a solid surface, then we call this gas-liquid chromatography if we're passing gases over it. So you can take a moment to pause the video and look at this table in more detail to figure out what the different types of chromatography are. No matter what type of chromatography we're talking about, we do have some general terminology where the stationary phase is confined in our column or a plate, and we have the mobile phase. When the mobile phase is going into the column, we call it eluent. Eluent in. Goes through the column, and then what's coming out is called eluate. The whole process of passing through the column is called elution. Our columns can either be packed with particles, as shown on the left. This is a scanning electron microscope image of a packed column for HPLC, or they can be an open tube. So you have a cross-section here showing the thin inner diameter of a open tubular column for gas chromatography. No matter what kind of chromatography we're talking about, we have a very basic principle of separation. And the schematic shown here is for a packed column, which is actually just showing gravity. You can pour mobile phase through it, or maybe you're pressing mobile phase through with high pressure. But you're starting with A and B. So we have this mixture of stuff, and we put in a little bit of it. So we have this tight band of A and B at time 0. And down at the bottom of the column, you have a detector that you're going to watch and see what's happening. It could be your eye if you had visible things, and that's how Michael Sweat actually determined chromatography, as he was using chlorophylls and pigments and watching the different colors of the bands come out. Over time, you're going to have different interactions between the two components. So in this case, A, the blue, is less attracted to the stationary phase, and so it's moving along in the mobile phase faster. And as time progresses, from time 1 to time 2 to time 3, you're going to get better separation. And at time 3, component A comes out, it elutes, and we would detect it. You can also collect it. So chromatography is often used for fractionation to collect out different components of your mixture. After that point, then analyte B will elute. In general, your instrument schematic is going to look something like this. You have a source of your mobile phase in the top left there. It's either a container of liquid or a compressed gas cylinder. You're going to put your sample in through a needle, a syringe, into some sort of injection port. And the details of all of these things will be elaborated on in future screencasts about gas chromatography and liquid chromatography. Your volumes are usually very small, somewhere between 1 and maybe 20 microliters are injected, and then it passes through your column where your stationary phase is held while it's being carried through with either your liquid or gas mobile phase. Then you have a detector, and there's a variety of those that are possible, and some sort of processor, computer, and out comes then your chromatogram. And your chromatogram is this plot of time versus response. And the very first thing to come out is the thing that likes or is less likely to interact with the column the least. It's really, really in the mobile phase, it rushes through, and then on towards things that are more and more retained by the column. The interactions between the analyte, the stationary phase, and the mobile phase can sometimes be a little abstract. So I like to give the analogy of shopping at an outlet mall. Now, I couldn't find a very good picture of an outlet mall that was linear, as most columns tend to be. So please just blur your eyes, close your eyes, listen to me for a moment, and think about this analogy. And if you're a student of mine, you can skip ahead, 30 seconds to skip the outlet mall analogy. But let's just imagine that we get a bus and load on a whole bunch of people, a whole bunch of college students, university students, and go to the local outlet mall. And I'm the bus driver, and I let you all out at one end of the mall, and I say, hey, I'll pick you up at the other side of the mall. Well, the amount of time it's going to take for you to get from one end of the mall to the other, from the beginning and the end of the column, where your mall is the column, is going to depend on how much you as a person, or you as a molecule, like or have affinity to the stores in the column. So one person might really love shopping for clothes. And if the mall has a lot of stores for clothing, it's going to take them a long time to come out the mall. They're going to go into the stores, they're going to interact with them a lot, they will spend a lot of time on the stationary phase, and not very much time walking through the hallways of the mall or being in the mobile phase. Whereas another analyte who's less interested in shopping for clothes and maybe has greater interest in sports goods wouldn't spend as much time in a mall that's full of clothing stores. If I put them on a different mall and on a different column that was more full of sports stores, then they would be the ones retained a long time. So you get the idea of this different retention of different people, different molecules, based on their interests. And interests, of course, don't really relate to molecules. Instead, what we're talking about is things like polarity or size. One of the things that we often talk about in chromatography is that we would have an equilibrium between analyte in the stationary phase and the mobile phase. So we can write an equilibrium reaction with our beautiful double arrows between analyte stationary and analyte mobile phase. And that has to do with how much time it's going to spend in the stationary phase versus the mobile phase. Because this is an equilibrium, we of course have to have an equilibrium constant, a coefficient, and we call this the distribution constant. Now that is a big K, not to be confused with the future K, which will be little, but we haven't gotten to yet. So it has to do with concentration of analyte in stationary phase divided by concentration of analyte in mobile phase. The retention time, if we look at the chromatogram, is as shown here. So we have some sort of detector signal versus time, and TR, retention time, is how long it takes to go from injection to the detector for any given analyte. There is something called dead time or void time, which is TM. Sometimes people will call that mobile phase time because that's how long it takes for an unretained species to get through the column. In our outlet mall analogy, TM is somebody who cares nothing at all about the stores and walks straight through the hallway from one end to the other, arrives back to my bus really quickly, sits in and listens to the radio with me. The T retention has to do with how long then, in addition, somebody is shopping in those stores. So we have adjusted retention time, TR prime, which is the actual time that each analyte is retained on the column. So time in mobile phase plus time on column equals total retention time. A few other important things. The retention factor. The retention factor for a different analyte, we have it written here for analyte A and for analyte B, is the retention time for that analyte minus the dead time over the dead time. So it's a proportion of how much more time are you staying in the column versus how much time it takes to come through. This is really handy because we often will change columns or change something about our setup, and I want to compare my results on my HPLC to your results on your HPLC. In that case, I really need to have an ability to scale the factors, and that's what your retention factor is all about. If you have a little bit longer column than I do, your mobile phase time, your dead time, will be bigger as well, and so things will scale based off of that. Another way to compare relative rates of migration, this is relative between analyte A and analyte B, is to look at retention in terms of a selectivity factor. That's abbreviated alpha, and it is basically a division of the retention factor for analyte B over the retention factor for analyte A. And if you'll recall from the previous slide, retention factor is our retention time minus the mobile phase time over the mobile phase time. And so we get this nice proportion here. We often will use these things, the selectivity factor on this slide, the alpha, and the retention factor, the K, in order to calculate the resolving power or the resolution of a column. And we'll talk about that in just a few minutes. Before we get into talking about resolution, let's first discuss the efficiency of a separation. This is usually discussed in terms of plate height, number of plates, and the Van Deemter equation. In the general schematic of chromatography that I showed earlier, if you were paying close attention, you would have noticed that the separation between peaks, A and B, increased as the time going through the column increased. And you also would have noticed that the width of the band increased as well. So we get broader peaks, shorter peaks as well, because the areas are the same, it's the same amount of stuff. And furthermore, if we have a change in separation and a change in peak area or width, then we can also talk about this in terms of resolution and efficiency. The peaks in chromatography are generally shaped like a Gaussian distribution, and that has to do with random variations of how long the analyte is in the mobile phase versus the stationary phase. When we have the peak of this curve, it's representing the average time that the analyte spends on the column. As you observed in the previous slide, the longer the column is, the more time we're in the column, the wider the peak is. There's also a relationship to how fast the mobile phase is going. And that relationship generally is the higher the flow rate, the narrower the peak. But that's not a very detailed explanation of this. Well, if we think about the spacing in time between two different peaks versus how wide they are, we can get to this idea of a column efficiency. And that is a characteristic describing how well we separate things. It comes from a thing called plate theory. And this is kind of a defunct theory because it's not at all how chromatography actually happens, but it's really handy in describing how efficient it is. In plate theory, we pretend that chromatography is a whole series of simple distillations, that you have a little tiny distillation distance, the h, the height of a plate, and there's going to be equilibrium within that space. And after there's equilibrium, then the analyte moves on, gets equilibrium again, moves on, gets equilibrium again, and so on. So, if we have a column that has a certain length, L, then it'll have a certain number, N, of plates, and each of those plates will have a certain height. These numbers can be really, really small for plate height, 0.1 to 0.001 centimeters, and the number of plates on a column can be really huge. If you want an efficient column, you want a large number of small plates. So how do we define plate height? Well, in the graph here, we see this Gaussian peak that has eluded at a certain distance through the column. And so we're now talking about distance. L is the length of our column. And we can look at what we have plus or minus 1 standard deviation from that Gaussian distribution and define our plate height as the standard deviation squared, or variance, divided by the length. This makes a lot of sense in terms of the physical arrangement of a column and with the idea that a plate is a real distance that an equilibrium occurs, but it's really not that useful in terms of chromatography because the fact is chromatograms are plotted as a function of time, not length. So this whole idea of variance in terms of centimeters squared means we have to do a conversion. But we can do that conversion. Conversions are totally possible in chemistry. We've got math. So what we will do is we will say, hey, standard deviation as a function of time, we'll call that tau. So we've got our beautiful Greek letter tau here. And we'll say, well, that's equal to standard deviation in terms of length divided by length over retention time. And that has to do with our speed. And we can then further make some math and say, well, 96% of the area under a peak could be estimated with this triangle, and we can think about the width, the baseline width of our peak, which would equal 4 standard deviations. So we get this idea of tau is width divided by 4. We plug that in, and we now have a definition of height equals length times the baseline width squared over 16 retention time squared. If you don't trust me, I'm sure you can find an instrumental analysis textbook that will go through all the details. We know the relationship between length and height equaling number of plates, so we have this other relationship for number of plates. Now I have to warn you right now, you have to be careful about how you're defining width. A lot of books, a lot of slides, including this one, will look at baseline width. But many times people will actually use the full width at half maximum, so halfway up the peak. And in that case, you'll have a different calculation for what the plate height is. Just make sure you're paying attention to what kind of width you're measuring and what kind of width you're given if you have a problem. All right, so things are broadened. We've got a standard deviation, we've got some variability in a Gaussian shape. Let's think about what governs the shape of the peaks. It turns out there are a lot of kinetic variables that describe how broad a zone or a band will be. And it includes how fast the mobile phase is flowing, which we'll abbreviate U. It includes diffusion coefficients, how quickly your analyte is moving both of the mobile phase and the stationary phase. It has to do with that retention factor that we defined a few slides ago. And it also has to do with how big the particles are if you have a packed column. If it's not packed, if it's open tubular, then we're talking about the diameter of the column there. And it has to do with the thickness of a liquid coating on the stationary phase, because most of our stationary phases are not solids, they're liquids coated as a thin film on a solid. Here we have two beautiful Nike swoosh type pictures or graphs for LC on top and GC on bottom. What's being plotted is the plate height on the y-axis and the flow rate of the mobile phase on the x-axis. There are two differences that you should notice between LC and GC. The first difference is that the x-axis, the flow rate, is a lot smaller for liquid chromatography than for gas chromatography. Because your mobile phase is moving more slowly in LC, it usually means that the GC is going to be faster. The other thing to notice is that the plate height for LC is also a lot smaller for GC, which would mean that the LC is going to be more efficient, right? Well, it would be if you had the same length of a column, but the LC columns are limited to definitely less than 50 centimeters because you get a really high pressure drop between the liquid being pushed into the column and the liquid coming out of it. In contrast, GC columns can be up to 50 meters long, which of course is 100 times difference. So the name of that curve that we just saw is the Van Deemter curve. And this equation in the middle of the slide here is the Van Deemter equation. We use this to optimize methods for chromatography or to select a best flow rate. And the terms that are part of this, we've got A, B, and C terms that describe all of these factors for efficiency, add up so there's a sweet spot, which is right under that big red arrow. And that's where you get the best plate height, because you'll remember a small plate height is better. because a small plate height means you get more separations in a given length, and you're going to get better, more efficient chromatography. So the U here is the linear flow rate of the mobile phase. And all of these other things are constants for a given column and stationary phase, and they depend on those kinetic parameters we saw a few moments ago. The A term is called the multiple flow path term, and sometimes it's also called eddy diffusion. It basically has to do with the fact that when you have a packed column, there's a variety of routes that the analyte can take to get from the start to the end of the column. Some of these routes, like the route that molecule 3 takes, are going to be a lot longer than the average, and some of these routes will be more direct, like for molecule 1. And this broadens the peak because it changes how long the analyte spends in the column. It really has nothing to do with flow rate, it has everything to do with the column itself. And if you want to get a better plate height by working on this term, what you need to do is make the diameter of the particles small, or have no particles whatsoever. A is going to be 0 for an open tubular column. On the top right of this slide, what you'll see is the miniature version of the Van Deemter equation, and I've circled the multiple paths term, which is just a straight line across with no variability based on flow rate. The B term describes longitudinal diffusion. So we know that diffusion is simply movement of analyte from high to low concentration. And in chromatography columns, you definitely have a starting zone of high concentration. It's your pure mixture that you put on there. So all the components in that mixture are trying to diffuse in the flow path and backwards, actually in the flow path, to areas of low concentration. This diffusion gets worse the longer you're in the column, the more time that passes. So if you want to get a better plate height, you need to increase the flow rate, which causes less time for this diffusion to happen, or try to get something with a smaller diffusion coefficient, so it's not going to diffuse so quickly. It turns out that for liquid chromatography, this is pretty much negligible because the diffusion rates are quite slow, and this tends to be more important in gas chromatography. In the Van Deemter equation, what you'll notice is that this B term, being B over flow rate, is going to have a small influence on plate height at high flow rates and be a huge dominant contribution to plate height at low flow rates. Because if you're really just moseying through that column, there's going to be a lot of diffusion. Here you have a number of diffusion coefficients for liquids. We have different solutes in different solvents. Mainly, this is stuff in water, and you can see that the diffusion coefficients are really quite small. Our last term, the C term, describes the equilibration time, or sometimes it's called the mass transfer term. What we need to think about here is that some of our solute, our analyte, is in the mobile phase and some is in the stationary phase. Going back to the mall analogy, what that means is some people who love clothing stores are in the hallway while others are in the stores. What you need to think about is that while somebody is in the store shopping, someone else who's very similar to them, another molecule of the same type, is in the mobile phase walking down the hall. In the picture here on the bottom right, we're starting out with a band where everything is together. We have a certain band width. We have some of it moving in the mobile phase along the direction of evolution, and some of it is retained at the stationary phase. If we have a slow equilibration between these two things, where we're not really getting analyte between the store and the hallway very quickly, then the group that's in the mobile phase is going to move on, and we've increased our bandwidth. Remember, bandwidth is really talking about what the plate height is. So the faster the mobile phase moves, the worse this is going to get, the more left behind some people or analytes will be in the store or on the stationary phase. So we want a very fast equilibration so that the mobile phase won't get too far ahead of the stationary phase. We do this by doing a few things. One of the easiest things is to have a thinner layer of liquid stationary phase. Another thing we can do is raise the temperature. It turns out that the Van Deemter equation, the C term, actually has two parts. One is due to mass transfer to and from the stationary phase. We call this CS, stationary. And the other one is mass transfer in the mobile phase, that's CM. To elaborate a little bit more on how we get smaller plate heights, we have to think about all of those kinetic properties. And so the table on the top right here is showing the term in the Van Deemter equation and all of the analyte properties that relate to it. I show those properties again for you on the bottom right. We already talked about multiple flow paths and how you need to have a smaller particle size, so it's proportional to dp. On this slide, the gamma and the lambda are just constants. We talked about how longitudinal diffusion is going to be decreased by having a higher flow rate and having a smaller diffusion coefficient in your mobile phase. And now we're going to talk about this mass transfer. So for both the mass transfer in and out of the stationary and mobile phase, you want to have a smaller retention factor because we have a function of retention factor. Also, you want to have faster diffusion coefficients for this term so that you will get to the interface more quickly. This is all about getting to the interface often so that equilibration can occur. With respect to the stationary phase, if you have a thinner liquid coating on the stationary phase, it'll take less time for the analyte to get to the interface of stationary and mobile phase, and so you'll have a smaller plate height. And for mobile phase, having smaller diameter particles, smaller diameter tubes for open tubular will also decrease the amount of time it takes to get to that interface. In summary, when we're talking about plate height, it might be helpful to wrap up comparing tubular, open tubular, and packed columns. The advantages of the open tubular columns are that there's absolutely no eddy diffusion path, no A term in the Van Deemter equation. So you're going to get better resolution because we can wipe that out altogether. Also, because there's no packing to resist the flow, you're going to have faster flow rates, which means you'll have less longitudinal diffusion, less of the B term. Lastly, you can get increased sensitivity and lower sample capacity. Lower sample capacity isn't necessarily a good thing. It means you have to use less sample, but it does mean that you don't have to have as much sample, which can be an advantage. The thing to remember with open tubular, and this is mainly for gas chromatography, is to keep the tubes narrow and use a very thin stationary phase so that you don't have a very large C term for the mass transfer. All right, now to resolution. Now resolution is the thing that we can picture because we're talking about how well separated our peaks are. So how do we measure resolution and how do we improve resolution? Usually, we can picture resolution a lot better than we can do the math. So the picture here on the right has 3 different resolutions. The top one is a resolution of 0.75, the middle one is the resolution of 1, and the bottom one is the resolution of 1.5. We're usually looking for 1.5 or larger as our resolution. Now there's a ton of arrows and things on here, but really what we're thinking about with resolution is what is the standard deviation of the peak as a function of time. And on the left side here, we have a simple equation where we're comparing the retention times of component A and B, the peaks we're trying to get the resolution between. And so we say, hey, 2 times the difference in time divided by the total time is going to be our resolution. Well, if instead of having the 2 on the top, we divided everything by 2, what that would do is make our bottom term, our denominator, be the average width. So we have this average width, and this is at the moment defined as the baseline width. And then we have our change in retention time. In the blue box down at the bottom then, we have change in retention time on top over average width on the bottom. You could also think of that as change in the volume of retention, but that's not particularly useful. And then the very last one, 0.589 times the change in retention time over the width at half average. That I like a lot, because the width at half average is your average full width at half maximum. And I mentioned earlier in this screencast that it's a lot easier to get the width of a peak halfway up. Okay, so we've got those crazy things, and you probably need to practice them to use the math. But how do we actually improve resolution? Well, if our original data looks like what you've got on top, and unfortunately that's pretty common to start out with, we've got 2 options. We can increase the separation between the bands and keep them the same width, that's B, or we can keep them in the same position and just decrease their width, that's C. Ideally, resolution should be between 1.5 and 10. If you calculated that your resolution is more than 10, you're pretty much wasting your own time. What that means is your peaks are so far apart from each other that you're just taking a lot more time with no benefit in peak separation. All right. So, to improve resolution, well, we've got a lot of calculations on this slide. It's the relationship between what is resolution, what is number of plates, you might have noticed the similarity here, and how do these two things relate to each other? Well, it turns out on the top right that resolution relates to the square root of the plate height, it relates to selectivity, and it relates to the retention factor. So let's think about each of these. To increase resolution, to make that number bigger, which is better, we can increase the number of theoretical plates. To do that, we can use a longer column, but that usually increases the time. Or we can change the parameters on our column, keep the same length, and just decrease our plate height. So that's all that stuff I just talked about, decrease particle size. You can also manipulate diffusion coefficients by decreasing the viscosity of the solvent by changing your solvent out altogether, or increasing the temperature to reduce viscosity. You can also change the retention factor by changing the temperature in the gas chromatography, or changing the relative composition of solvents in LC. And lastly, you can change selectivity factor. In this case, you would try different solvents for LC, again, adjust that column temperature. You can change the actual composition of the stationary phase. What's that basically like? It's like letting the students out in a different outlet wall. If you've got two things that are too similar, maybe give them different stationary phases, so they'll have different affinities for them. And lastly, and this is a huge topic in the literature, is to do chemistry, to change the molecules. So this plot here is showing what happens when you do vary the relative proportions of the solvent. This is for liquid chromatography. And you'll see along the x-axis, we've got a number of times where it says inject. And with inject, you then have several peaks after that. There are 5 components here. And it's showing you a sequence. So 70% methanol, 30% water has almost everything coming out right on top of each other around, I'd say that's 2 minutes. Decreasing the methanol, you're starting to see some separation of things around 10 minutes. This is the second injection. With your third injection for half and half methanol water, you've got things actually separated, and that's lovely. Moving it to 40% methanol didn't do anything for you. You already had separation at 50% methanol, and now you're just moving things out and wasting time. Cool. So a last few comments here. The general elution problem. Typically, what we have is a large mixture, more than 2 things in it, maybe 6 for the sake of discussion. And you can optimize the resolution for different peaks here. From top to bottom of this plot, we've optimized the resolution for the first 2 peaks, for the last 2 peaks, and for the middle 2 peaks. And you've got various trade-offs between time and resolution. Resolving the first 2 peaks resolves everything in A, but it's also taking a lot of time. With the other ones where you're just trying to resolve the later peaks, then your early peaks are getting smashed on top of each other and you have bad resolution. So it's difficult to find parameters that will give good separation of all components in a mixture without wasting a lot of time. The way we solve this elution problem is to use gradient elution. Sometimes it's called solvent programming in liquid chromatography, or temperature programming in gas chromatography. Liquid chromatography is all about the polarity of the compound, sometimes the size. And if you can change the polarity of your mobile phase immediately after, in this case, the first 2 things elute, you can let the first 2 things elute as an A, and then ramp up to the conditions in C to let 3 and 4 come out, and then ramp up to the conditions in B to get 5 and 6 to come out. In that case, then you'll get good resolution in a minimum time. The same thing happens in GC, but GC is all about boiling point, and so you'd want to ramp the temperature in order to change things based on their boiling point and volatility. One of the other reasons why you might do gradient elution is that you sometimes get sticky compounds that are left behind on your column. And over time, these compounds will build up and they'll just hang out there, and it reduces the capacity of your column. So it's sometimes just a good habit to ramp up to a strong mobile phase composition, or to ramp up to a high temperature in order to clean that column off at the end of every sample. Okay, here we go. Analysis. The qualitative analysis for molecules is all about having a characteristic retention time. If I'm using the same set of conditions, a given molecule is going to elute at the same time every time. There's some leeway as things change a little bit in my conditions, but they have characteristic retention times. Now, what you need to realize is this is just one piece of information about that molecule. Having a peak at a given retention time is not confirmation that the molecule is there. You could have other things that elute at the same time and interfere with the analysis. But while having a peak is not confirmation of its existence, absence of a peak does mean the compound is absent, or rather is below the detection limits. So the thing is that chromatography doesn't tell you much about what a molecule is. It's just not that specific. You need to have some other identification tool, some detector that's going to tell you what the molecule is. Infrared spectrometry, NMR, mass spectrometry, all of these things are so much more specific than chromatography is. In fact, some people will say chromatography is not an instrument at all, it's just a separation tool, and you should have a more specific mode of detection paired up to it to really identify what something is. Lastly, quantitative analysis. Quantitative analysis with chromatography is simple. If you have a detector that's going to respond to the compound coming off the column, you can simply look at the peak height or the peak area and relate that to the amount of material. Generally, you want to use peak area because it doesn't depend on how broad the peak is. You need to do a calibration curve with a series of different concentrations of standards external to your sample, and use that to get the response of your detector to the compounds. Also, it's very, very common to use internal standards to account for the variation in sample volume that you inject. This is because you may have a set injection of 20 microliters, but it might vary a little bit below and above that, and you want to know that the change in the area of your peak has to do with the concentration changes, and not to a simple change in how much material was put on the column. Now, some handy formulas. These two slides I'm going to flash up real quick, and you can pause them and look at them at your leisure. It's a summary of the most important terms and equations from the textbook, which is SCOOG, Instrumental Analysis. Thank you for your attention.